And you can see this data is from 1960 to 2020, so 60 years of data, and this is I think this is a quarterly data. Yeah, so this is a quarterly data over 60 years. So a couple of things that you can immediately see from this raw plot. So you can see this increasing pattern. And this increasing pattern, sort of like a quadratic increasing pattern. So that's might suggest that we want to take a second order difference. And moreover, you can see that here we have this seasonality pattern, right? So like up, down, up, down, up, down, up, down. So this has a very clear seasonality pattern. Okay. Yeah, and moreover, you can see that there's not much heteroscedasticity in this model, in this time series. Okay, so the variance of the data are pretty much constant over this 60 years. Okay, yeah, and we also see that there might exist some seasonality, like non-stationary. Okay, there are some like seasonality increasing of the data. Okay, yeah. So by looking at the raw data plots, we can see there's no heteroscedasticity. There is stationary. No, I'm sorry, the data is not stationary. Has a quadratic pattern. Stationary heteroscedasticity. So that's what we can immediately see from this raw data plot. And I checked the ACF of this data. And you can see that the ACF does not die very quickly, and it's actually very large. Okay, and this is not surprising because of this increasing pattern. We will definitely not see a good ACF plot. Okay, so now let's try some transformation. Okay, yeah, yeah. So let's first do like this transformation. So you can see that after this log transformation, there's not much difference between this plot and the raw plot. Okay, and this also makes sense because by just looking at this raw plot, we do not see much heteroscedasticity. So when you take the log transformation, like the log transformation basically like makes the right skewed data more to a normal distributed data. And because we like our original data is pretty much like normal distributed, so if you take log, there shouldn't be much difference. Okay, so that's what we see. Okay, so now based on this, let's just forget about like the log transformation for a moment. Let's just say like there's no heteroscedasticity problem in this time series data. Okay, so now let's do some transformation and check the ACF plot of each transformation. Okay, so this is the first transformation we consider. So this is a seasonality transformation. No, I think this is a yearly data, a monthly data, not a yearly. I'm sorry. So yeah, this is a monthly data. Okay. Yeah. Anyway, so let's do this seasonality transformation. So we just like take the 12th month transformation, and that's the plot we got. Okay. And let's check its ACF and see how the ACF looks like. So you can easily see that this ACF is not very good. Okay, so that also makes sense because this transformation, after this transformation, you can still see an increasing pattern here. Okay. So that means if you draw the ACF of this time series, then you won't get a very good ACF plot. Okay, so that means the season seasonality transformation does not fix the problem. Okay. So now how about now we include the regular transformation? So this command does two things. First, it does a regular transformation, so which is this diff part, and it also does a seasonal transformation, so which is diff 12. Okay. And this is the plot that we got if we do these two transformations simultaneously. Okay. You can see like the mean is pretty constant. And it seems that there is not much seasonality pattern here, seasonality trend here. And let's check the ACF to confirm this. Okay, and here's our ACF plot. So you can see that after leg number 1, so actually which is leg number 12, okay, you can see that everything, like all the legs after leg number 12 is pretty much within the confidence interval, okay? So this tells us what? So this tells us that the ACF plot first is good, but we still have some seasonality pattern in this time series. Okay, so we do not have those seasonality trend, but we still have some seasonality pattern. So if there's no seasonality pattern, then this ACF plot should be, let's say that it dies like in leg number 2 or leg number 3. But however, we see like this very large leg in leg number 12, and we know that our data is a monthly data. So that means there still exists some seasonality pattern in our data set. Okay, so which is fine. We will build up that seasonality pattern into our final SARIMA model, which is fine. But what we just now looking at what we can now get from this ACF plot. So that means our two transformations, the seasonality transformation and the regular transformation, works very well. Okay. So this says that the first order transformation and okay. So to verify that we do a good job, let's check how about if we transform this CO2, this carbon dioxide, by taking the log. Okay, so let's do the same thing, which this is that we take the regular difference, we take the seasonality difference, and we take the log on the time series. Okay, and that's the ACF plot we got if we do like this 3 transformation together. So you can see like this ACF plot and the ACF plot without the transformation are pretty similar. Okay. So that's again suggests that's the lower carbon dioxide time series. Okay, so this suggests that's the log transformation. Okay, so given this, let's just proceed our model without taking the log transformation of the carbon dioxide. Okay, yeah, and I also verify my data set by doing the quarterly difference. Okay, and I want to see if I do the quarterly difference instead of the monthly difference, how the data looks like. And this is what I got if I take the first order difference and the quarterly difference. Okay, so this is the raw data I got. So clearly there's no trend here. The mean is 10, but I can tell that there still is some seasonality trend here, especially you can see like here, like those things that within here, there's like very clear like seasonality trend. And if I plot the ACF, you can see this is like the ACF plot of this quarterly like difference data. Okay, so obviously this ACF plot is not very good. Every leg is outside this confidence interval. Okay, so this suggests that the first order difference and quarterly difference are not good. Okay. Yeah, so that's part one, the data transformation part. We try a bunch of data transformation, and it seems to me that the first order difference transformation and the seasonal, and the, let's say the monthly transformation, and the monthly transformation are the best. Okay, the ACF plot is the best, and we actually do not see any trend, any heteroscedasticity, any seasonality pattern, like any seasonality trend in the raw data plot as well. Okay. So based on this, let's identify our model, where the time series we take is the first order difference and the monthly difference data. Okay, so this is the ACF and the PACF plot we got. Okay. So what do you see here? So the ACF plot, we already seen that. We see that there is a huge lag here at lag number 12. And after lag number 12, all the lags, all the ACF lag sims are within this confidence interval. Okay. However, for the PACF plot, you can see that there's large lag at lag number 1, lag number 2, lag number 3, and also lag number 4. And moreover, you can see there's huge lags here, like lag number 11. I think this is lag number 23. Here is like lag number 35, and this is lag number 47. Okay, yeah. But anyway, you can see that for the PACF plot, it seems that this PACF plots are tails off every 12 legs. Okay, but for the ACF plot, it just cuts off after leg number 12. Okay, yeah. So thinking about that, like what model might be a good model to capture this ACF and the PACF plot? So if you remember our previous class, the ACF and the PACF plot suggest that as ARIMA 0, 1, 1 times 0, 1, 1, 12 might be a good starting point. Okay. Yeah, the reason is that this ACF plot cuts off at leg number 12, and we see this seasonal tails off for the PACF plot. Okay, so that's why we think that the S-ARIMA 0, 1, 1 times 0, 1, 1, 12 might be a good starting point. Okay, but there might also be some other possibilities. Okay, so for example, someone might suggest that, okay, I see a large lag here at the ACF plot. So does that mean that we might also want to fit an AR1 model here? So how about like an S-ARIMA 111 times 0, 1, 1, 12 model? Okay, yeah, and someone might think, how about I increase the order of the model a little bit? Okay, so instead of fitting like a 0, 1, 1, 12 model, how about I fit a 0, 1, 2, 12 model? Right, because you can see here that we, like for this PACF tails off, like not only leg 1 is very large, also leg number 2, leg number 3, you can see here leg number 2, leg number 2, leg number 3 are also very large. So how about I increase the order of the MA part a little bit, and let's just do a S-ARIMA 0, 1, 1, 0, 1, 2, 12 model. Okay, so we will also check like all those models in our analysis and find the best one. But for now, let's just start with this S-ARIMA 0, 1, 1, 0, 1, 1, 12 model. And this is a code that we'll use for this fit. Okay, so the PDQ, small PDQ is the regular ARIMA model. The order is 0, 1, 1. Okay, and yeah, and if you take like the diff carbon dioxide at first, then it's just 0, 0, 1. Okay, but now we just use the raw data, so we will use like 0, 1, 1. Okay, and for the seasonality ARIMA part, we also fit a 0, 1, 1 model, and the seasonal part is like 12 because it's a monthly data, and we find like the monthly difference is much better than the quarterly difference. Okay, yeah, and after some calculation, this is what we got. Okay, so let's do this. Okay. Number significance. So clearly, both the MA part and the seasonality MA part are statistically significant. Okay, so this is good. And number two, we want to check. We want to check if this is a valid ARMA model. Okay, so to check if this is a valid ARMA model, this is a little bit tricky here because this model is a combination of the ARIMA model and the S-ARIMA model. Okay, so what is the actually like what is like there's like no AR coefficient, right? So everything here is MA coefficient. So for the AR coefficient, we just put 0 here because there's no AR coefficient. And for the MA coefficient, it actually like consists of 3 parts. Okay, not 2 parts. It actually consists of 3 parts. Part number 1 is the regular MA, so this MA1, and we know this is MA1, so we put negative 0.3875 here. Okay. And we also know that there's a seasonal part, okay? So the seasonal part, the coefficient for the seasonal part is negative 0.8641. And this is at leg number 12, okay? So what we put is that we put 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All this coefficient equal to 0, right? And the coefficient number 12 is equal to negative 0.8641. Okay, so that's part number 2. And moreover, there's actually a part number 3 of this MA model. So if you like recall last class notes, because we have like this MA1 and MA12, and if you combine these 2 parts together, there's actually a MA13. So the coefficient of the MA13 is actually not equal to 0. It is equal to the product of the coefficient of leg 1 and leg 12. Okay, the leg 1 is this number, the leg 12 is this number, and the product of it is this number, 0.3348. So the coefficient of leg 13 is 0.3348. Okay, just be very careful here. Okay, so once you have a ARIMA part and an S-ARIMA part, then the coefficient of the MA or the AR is actually a little bit tricky. You need to not only take care of the regular MA, the seasonal MA, you also need to take care of the product of the regular MA and the seasonal MA. Okay, so now this is the coefficient of the MA part, and let's check if this is a valid ARMA model. So we first check if this can be written as an MA infinity model. And of course, this can be written as an MA infinity model because there's no AR part. Everything is MA. And we already know the coefficient of MA. So you can easily see that the first coefficient, negative 0.39, coefficient number 12, negative 0.86, coefficient number 13, 0.33. Okay, and all the other coefficients are equal to 0. So this suggests that this model can be written as an MA infinity model, and the coefficient of that MA infinity would be less than infinity. Okay, and now let's check whether this model can be written as a valid AR infinity model. Okay, so you can see because of the seasonality here, I increase the order of the coefficient to 500. Okay, and I see that maybe here after say like coefficient 421, all the coefficient after coefficient 420 are all zero. Okay, yeah. So this is not easy. You need to increase the order of the AR coefficient to make sure that your model actually converge. Okay. So they suggest that our model is a valid ARMA model. It is causal and invertible. Okay. I put this command here just to show you is that if you do not have like this leg number 13, you will find this is not a valid ARMA model. Okay, so if your MA coefficient, if you only put the MA1 coefficient and MA12 coefficient here and forget about this MA13 coefficient, you will find it is not a convergence model. You see that the coefficient diverges actually, right? Very easy to see, it diverges. The reason is that you forgot this MA13 coefficient. Okay, so in your analysis, please make sure that you have this MA13 if you are considering this like MA1 and SMA1 model. Okay. Right, so that's check number 2, and let's check number 3. So check number 3 is to check the parameter redundancy. Okay, so because this model does not have a AR part, so this is of course like the most simple model. There's no parameter redundancy problem here. So no AR implies no parameter redundancy problem. Okay, very good. And number 4, let's check the residual plots. Okay, so the residual plots are given here. So you can see the standardized residues are not bad. The ACF of the residues, all of them are within the confidence interval, which is also good. And this is a normal QQ plot. So most of the observations are within these shaded regions, which is also good. Yeah, and for the LB statistics, we can see that after leg number 5 or maybe number 6, everything is statistically insignificant. Okay, so this suggests that our model might be a accept model, but there might be some problems in the first 4 legs. Okay, so the conclusion is that the residual plots are good, but the first 4 legs of the LB statistics are not very good. Okay. And finally, let me record the AIC and BIC of this model. So the AIC of this model is 0.51. Okay, and the BIC here is 0.5405. Okay, so I just record this for future comparison. Okay, so that's the diagnostics of this SREMA 011 times 01112 model. So overall, I think this is a good model. The only thing that I'm a little bit concerned about is this first 4 legs or maybe 6 lags, I don't know, like of the LB statistic. Okay, so given this, so how about we do some other models and see if those other models is better than this model, or if other models can address this LB statistics problem. Okay, so then that's our model comparison. Okay, so the first model that I decide to compare with the starting point model is this SARIMA 1110112 model. And the reason that I consider this model is because the ACF plot here, we have a large lag here. Okay. Okay, so given this, let's run this model. Yes. Okay. So couple of things we want to check. So number one is that we want to check the coefficient of significance. So you can see that here, everything is statistically significant at 5%. Okay, but if you are looking at 1%, then this AR1 coefficient is not statistically significant. Okay, but usually we are just doing like 5% check, so I think this is fine, but this is just like marginally significant. Okay, and number two is that we want to check if this is a valid ARMA model. Okay, so to do this, I use these two codes. Okay, so now here you can see that we not only have this MA part, but we also have an AR part. But the AR part is easy. It's just like the regular AR part. So the coefficient of this AR is just like 0.1941. Okay, but for the MA part, you still have like 3 components here actually. One is the MA1, the second is MA12, and the third is MA13, which is equal to the product of MA1 times MA12. Okay, and let's run this and see what we got. Okay, so clearly this model can be written as a valid MA infinity model. And how about a AR infinity model? Again, you can see like this can be written as a valid AR infinity model, so which is good. Okay, so this says that our model considered here is a valid ARMA model. It is causal and invertible, and we include the MA13 coefficient in the command. So this is a good command. This is like the good code. Okay, and number 4 is that we want to check if there's any parameter redundancy. So note here, since right now we have like this AR part, so there might be some parameter redundancy from here. Okay. So let's first check the AR. So the polynomial root of this AR is equal to 5.16, or I'm sorry, 5.15. Okay. And the polynomial root for this MA coefficient is this. Okay. So you will see that the MA coefficient again here is that you need to put like 10 zeros between leg number 1 and leg number 12, or maybe 11 zeros. Okay, yeah. But anyway, this is the polynomial root of the MA coefficient, and I think I'll compare it, and I do not find like this any of these 13 polynomial roots are similar to are similar to this 5.1519. Which is the polynomial root of the AR coefficient. Okay, so this suggests that there's no parameter redundancy because all the MA roots are not equal to AR roots. Okay. And now let's check the residual plots. Okay, so the residual plots, you can see the standardized residuals, ACF plot, normal QQ plot, all of them are pretty good. And we can see that for the LB statistics, it seems that only the first leg is a little bit statistically insignificant. It's a little bit like marginally insignificant. And all the LB statistics after all the legs, the LB statistics of all the legs afterward are pretty good. So this is certainly better than the like our first model, right? Okay, and finally, let me write down the AIC and BIC here. Okay, 95 BIC 46. Okay, so you can see that the AIC for this model, model number 2, is smaller than the AIC for model number 1. Okay, but the BIC for model number 1 is actually smaller than the BIC of model number 2. Okay, and the BIC does not agree with each other, so we cannot say much about by just looking at the AIC and the BIC. However, I think the residual plots of model number 2 is better than the residual plots of model number 1. Okay, so for now, I think I perhaps will think that model number 2 is better than model number 1. Okay, yeah, like 1, 2, 3, these 3 criteria, they are pretty much similar. And criteria number 5, I think similar, and criteria number 4, I think model number 2 is better than model number 1. Okay, so for now, let's just think that, okay, I will use model number 2, but this is not like a ending point. So I want to try some other models and see if those models can be better than model number 2. And what I do here is that I consider this 111 times 11112 model. Okay, so I also give like the seasonality part of the AR order number 1. Okay, and I run this model. Okay, and these are the coefficients I got. So you can very quickly notice that the coefficients are not all statistically significant. Okay, so the SAR1 coefficient is not significant. So this is what? Because this SAR1 part is the new part that we introduced in this model, and we find its p-value is pretty large, right? So that says that this SAR1 coefficient or this SAR1 variable perhaps is not very important in explaining our time series. Okay. And how about, is it a valid ARMA model? Let's run this. Yeah, and again here, because we are doing like this AR1 and A times AR112 parts, so for the AR coefficients, you not only have lag number 1 coefficient and lag number 12 coefficient, but you also have like lag number 13 coefficient. Okay. All right, so let's run this code. Okay, it seems that, okay, this can be written as a valid MA infinity model. And how about can it be written as a valid AR infinity model? And it seems it is yes. Okay. Okay. And also let's check the parameter redundancy. Okay. So this is the AR polynomial roots, and this is the MA polynomial roots. Okay, yeah, and I also check by myself, and I do not find any 2 roots are very close. The only thing I find is that here, one of the AR root is about approximately 1.607. And there is a root here, root number 13 for the MA polynomial. It's like 1.789. So these 2 are the only 2 that I found are close to each other, but they are not that close. It's about like 10% difference. Okay, but for the other polynomial roots, I found they are quite different. So I think I can conclude that there is no parameter redundancy problem. Okay, the model we consider is the simplest model. It's the simplest model. Okay, and how about for the residual plots? It seems to me that everything is good. The first leg is a little bit statistically significant, and all the other legs are statistically insignificant. So I think the residual plots are good. And now let me write down the AIC and the BIC. So the AIC here is 0.5222, and the BIC here is 0.5536. Okay, you can easily see that the AIC and the BIC of this model number 3 are larger than the AIC and the BIC of model number 2. Okay, this actually makes sense, right? Because we find that the SAR1 coefficient is statistically insignificant and very insignificant. So that means we actually add a redundancy explanatory variable in the model. Okay, so that means your AIC and your BIC should be large, right? You just include some like redundancy information in your like information criteria formula. So you will have a large information criteria, and this is what we got. Okay. So by comparing model number 3 and model number 2, I can easily conclude that model number 2 is better than model number 3. Okay. Because the coefficient of model number 2 is better, and the AIC and the BIC of the model number 2 is also better than model number 3. Okay. Yeah, and finally, I also consider a couple of like more like models. So I consider like this as a Riemann model, whereas it is like 111012, and I find the AIC and the BIC of this model is 5.2225537. And I also consider some other models. For example, this one I consider is 012011. So I just increase the order of like our starting point model a little bit and see if we can have some like find some better models. And it seems to me that no, we cannot. So for example, this model I find is 5.209 and BIC is 0.5461. Okay. And for this last model, yeah, it takes some time to run. And the AIC I find is 0.5212 and BIC is 0.5527. Yeah, so I consider this couple of more models, and I realize that all these models have larger AIC and BIC than my model number 2. Okay, so this perhaps suggests that my model number 2 is the best model. And just recall the model number 2 is 111 times 01112 model. This is perhaps our model to model this carbon dioxide concentration. Okay, and finally, if you want to use this model to do forecasting, you can definitely do that. So in this example, I do a 60-period forecasting by using this model, and this is what I got. Okay, so you can see that this is the red points are the forecasting plots, and this black points are the other raw data. So you can see that if we do not control the CO2 concentration, then it will increase all the way to infinity. This is not what we want. Okay, so if you want to use this model to have some policy implication, I think it's very straightforward. It's that if we do not do something to control our climate, then we will have an infinite CO2, which is very bad. So this model might suggest that we want to maybe use some like reusable energy or stuff like that to reduce the emission of the CO2. Okay, so that might be a policy implication if you do this forecasting and you can like tell other people. Okay, which I think is very interesting. Okay, yeah. So this example I think is a pretty comprehensive like analysis of a time series, a S-Riemann model built up. So any questions here? Okay, so yeah, if there's no questions, I want to talk a little bit more about like the model fit. Okay, so yeah, these are some things that I see from your research project. So so this example, the model fit is very good. Okay, but it is possible that your model fit, even like you try a bunch of like different S-Riemann models, you still cannot find a very good model. This is highly possible and very possible if like your data is not that very clean data. Okay, so there are actually several ways that we can do to improve the model. We discussed that we can re-identify the model. So to re-identify the model, what we do is that we just look at the ACF plot and the PACF plot and see if there's any other models that can match the ACF and the PACF plot. Okay, so that's what we've seen already. And another way is that you can actually retransform the data. Okay, so in this data analysis example, we do not do like the log transformation, but in some cases, I think in most of your research projects, you do the log transformations and you tell me that the log transformation is better. Yeah, but actually there are some other types of transformation and which I want to talk a little bit today. Okay, and in that example, you will see that those different transformation can actually make the transform the data much better. Okay, and the number three, I think is perhaps is the most important thing, is that you need to take care of the outliers if you find that your model fit is not very good. I see like in some of your examples, you have like, especially like in those recession period. So for example, like the 2008 financial crisis, or in the like in this COVID-19 pandemic, you will see like some large variations in the data, and those would be considered as the outliers sometimes. So and if you include those data in your analysis, you perhaps cannot find a very good model. So I want to talk a little bit more about like how to take care of like those outliers in today's class. Okay, so these are the two things that I want to talk a little bit more. One is to retransform the data, and the third is to take care of the outliers. Okay. So I want to use this example, which I think is a very interesting example. It's an example from the BK textbook. Okay. Yeah, and I think this is a very famous example. Okay, so in 1973, I think there's two guys, Chatfield and Proto-Thero, they want to like study like company X monthly sales of a single product. Okay, so this is monthly sales of a product from January 1965 to January 1971. Okay, so let's start from the beginning. So you can see there's a trend, an increasing trend. There is some seasonality trend. There is some seasonality pattern, and moreover, this data is not does not have constant variance. So we have like this heteroscedasticity pattern here. Okay, so the first transformation that we want to do is to, I think here, right? The first transformation that we want to do here is to take care of those heteroscedasticity. Okay, so in the textbook, it considers three transformations. The first transformation is a log transformation. Transformation 2 is the sales to the power 0.25. And transformation 3 is a sales to the power 0.5, so which is a square root transformation. right? So what can you see from this transformation? So the sales is definitely not very good. We see that the variance becomes larger, okay? However, for the log transformation, you can see it is also not very good. It seems to me that this variance becomes smaller, okay? And moreover, for this square root transformation, you can see that it also does not take care of the data very well, right? The sales transformation, the square root transformation, the variance is still increasing, okay? And it seems to me that this sales to the power 0.25 transformation is perhaps like the best transformation, right? So you do not see like those heteroscedasticity in this time series when you take that transformation, okay? So, yeah, so I think the right transformation that the textbook does is to do this 0.25 transformation, okay? And yeah, let me, right here, yeah. So I think the textbook does this 0.5 transformation, and it plots the ACF plot and the PACF plot. Okay, so that's the PACF plot it got, and this is the ACF plot it got. Okay, I think this figure. Okay, right. Figure number 1 is just the 0.25 transformation, and figure number B is the 0.25 transformation together with the regular difference, first order difference. And this figure number 3 is the seasonality. It's the monthly difference plus the further difference plus the 0.25 transformation. Okay, and you can easily see that we will use this last plot. So we will use seasonal. We will use a monthly transformation, first order transformation, and we will transform the data to the power 0.25. Okay. So this is the ACF plot, and this is the PACF plot. Okay, so I think you should be very good at this. And I think by looking at this plot, the textbook suggests that we will use a AR1 SMA12 model. Okay, so that is the RIMA 110 times 01112 model. Okay, yeah, just by looking at the ACF and the PACF plot, you can think that this is your starting point. Okay, then the interesting part comes. Okay, so we estimate this model, we find the coefficients are statistically significant. However, we notice that all the LB statistics, the p-value are less than 0.5. So everything you can see here is less than 0.5. Very interesting, right? Right, so very, very interesting. Everything is less than 0.5. So this suggests what? This suggests that this is actually not a very good model. Okay, so it rejects the model. Okay, like even though like the residual plots are somewhat fine, you can find some like large lags here, but it looks not that bad. Okay, and this as a residuals looks not that bad. Okay, and the coefficients are both statistically significant. But what we find that all the LB statistics are statistically significant. Okay, and you know what? Like this is actually what Chatfield and Proto-Theroux they found in their analysis. Okay, but they use like this log transformation. They use like this YT to the 0.25 transformation. Okay, yeah, and they actually raised this. They actually give this question to Box and Jenkins. Yeah, and also like Wilson. Yeah, so the Box is the very famous statistician. Okay, so they say that why I have like everything else, everything good except this LB statistics. What causes this? Okay, right. And in their response, they said that it might be due to the inappropriate over transformation using the log. Okay, so what's then Box and Cox suggest that is instead of using this log transformation or the transformation of yt to the 0.25 or even yt to the 0.5, let's use this general transformation. Okay, so this is the general Box-Cox transformation. So it depends on this parameter lambda. If this lambda is equal to 0, then this is just the log transformation that we already use. Okay. And if this lambda is not equal to 0, this is a transformation that we will use. Okay, and this compromises the 0.25 and 0.5 power as its case. And this lambda equal to 0, this log transformation here is just a special case of this Box-Cox transformation. Okay. Yeah, and moreover, Box-Cox, because of like the variance of the transformed data not comparable for different values of lambda, and the scale depends on lambda. So the Box-Cox like suggests using this like rescaled transformation. Okay, so this rescaled transformation is basically like transformed, like rescaled by this white dot. Okay, there where this white dot is like the geometric mean of the sample. Okay, anyway, like the software can do all this for you. Okay, so no worries. Okay, so this is a Box-Cox transformation, and the things that you need to choose this lambda. Okay, the things that you need to choose this lambda. If this lambda is equal to 0, then this is just a log transformation. If this lambda is not equal to 0, it's just not log transformation. And in our previous analysis, we just like pick this lambda arbitrarily, right? In most cases, we just like pick this lambda equal to 0, which is a log lambda. And I see in some of your research, some of you do like the 0.5 transformation, the square root transformation, which is also very good. But again, like this square root transformation is something that you pick randomly or arbitrarily, right? It's just like one case of this Box-Cox transformation. Okay, so the question is that what is the optimal lambda? Okay, so what is the optimal lambda? Is the log transformation the optimal, or is the square root transformation optimal, or is that there's any other lambda optimal? Okay, and to choose this optimal lambda, we can follow a very easy step. Okay, so what we do is that we will transform like the data with all lambdas, and we will refit those, and we will fit like those time series by using like each lambda. And then we will find its residual sum squares. Okay, so let me show you this figure. Okay, so in this figure, the textbook considers a huge, like a very wide range of lambda from -0.5 to 1. Okay, and for each lambda, it calculates the sum of the residual errors. Okay, so you can see that, for example, one lambda equal to -0.5. I think this is a log 10 of the residual sum of squares is like approximately 20,000. Okay, and however, you can see if this lambda is equal to 0, which is log lambda, then the residual sum of squares is approximately 80,000, so which is definitely smaller than this 200,000. Okay, and it finds that when lambda is equal to 0.16. Okay, when lambda is equal to 0.16, the residual sum of squares is the smallest. Okay, so you can see this like quadratic graph, and you can see this is a lambda that has this smallest sum of residuals. Okay, so you can see now this optimal lambda, which is equal to 0.16, is very different, or not very different. It's different from what we use, right? So what we use, so in our previous analysis where we got all this small p-value of the LB statistics, we use the lambda equal to 0.25, right? And in the Chatfield and Prothero, their analysis, they just pick lambda equal to 0. Okay, but we find that the optimal lambda is actually equal to 0.16. Okay, so now how about we fit the data by using this optimal lambda equal to 0.16. So what do we got? So you can see that again, the coefficient are statistically significant. And more importantly, we find like the leg number 12, leg number 24, the p-values are both are like approximately 0.05, so 5%. So that means they are like marginally insignificant at 5% significance level, right? So this is not very perfect, but this is much better than what we got early, right? You can see this is what we got early if we use a lambda equal to 0.25. So all the p-values are smaller than 0.05. But right now we see that at least 2 of the p-values are at least equal to 0.05. Okay, so which is better. Okay, yeah, so that's, yeah, and here's like the residual plots of when lambda equal to 0.16. So everything here is good. Okay, so that's one possibility that Chatfield and Prothero have in their original analysis. It is that they over-transform the data a little bit. Okay, and that's actually the response from Box and Jenkins. Okay, so that's one possibility, but we still see here that these p-values are not very perfect. And even if you look at like number 36 and like number 48, they are too small, right? Okay, so the other possibility that got those very weird p-values of the LB statistics, and we can, how about we check the what I mentioned, okay? It's because if you just like take that outliers away, then your time series is actually not a valid time series. Okay, so suppose that your outlier is observation number 50, okay, and you throw number 50 away. Then you basically has 2 time series. One is 1 to 49, the second is 50 to 100. You cannot combine these 2 time series together because you just threw away observation number 50, okay? But the lucky thing here is that the outliers we have here is number 74, okay? So which is the one of like the last points of our observation. I think here we only have like, you see, we only have like 77 observations. So number 74, if number 74 is outlier, so how about we just throw away number 74 to number 77 and use the first 73 observations for our time series analysis. Okay, so this is fine because it only affects like 3 or 4 data points. However, if your outliers is in the middle of your time series, then doing this outlier analysis is much complicated. Okay, so now let's say that how about we throw away observation number 74, okay? And we again find the optimal lambda, and here's optimal lambda is 0.23, okay? So which is pretty close to our original lambda. We choose 0.25, okay? So we use this lambda equal to 0.3, and we use like only like the 72 observations for our analysis, okay? And this is what we got. Okay, so you can see this, the p-values of this LB statistics are much, much better than our previous analysis, right? Leg number 12, leg number 24, leg number 36, all of them are statistically insignificant, okay, and very insignificant, not like those marginally insignificant, okay? Leg 48 is still 48 still has some problems. But we can at least tell that if we throw away the observation from 74 to 77, yeah, and here this is just use lambda equal to 0.25. I think there won't be much difference if you use lambda equal to 0.3, which is the optimal lambda. Okay, so if we just use lambda equal to 0.25 and throw away the outliers, we got a very, very good LB statistics. And again, the coefficients are statistically significant, and the residual plots are not bad. I think it's good. Okay, and you can obviously like further do this like outliers analysis. So for example, it's like in this graph, it says that it seems like observation number 64 is an outlier. 64 here, 64 here, 64 here. So how about we throw away 64 to 72 and only use the first 63 observations for the like further analysis. So you can do this like iteratively and until you find like everything is good. Okay, so for example, maybe if you throw away observation 64 and perhaps you can get like the p-value of leg number 48 is statistically insignificant. Okay, yeah, but yeah, these are some final thoughts. So whenever you find like your model is not very good, there are a couple of ways you can refit your model. Number first is that you refit, like you re-choose the order of your model. Number two is you do some other transformation. And number three is that you do some outlier analysis, okay? Yeah, but anyway, and here it says that it seems that there's two very different model. This model, lambda equal to 0.25, but only uses 72 observation, is pretty similar to the model with lambda equal to 0.16, but with all the time series. Okay, 77 observations. So it seems like these two models are pretty similar. And this comes to the George Box. The Box, very famous statistician. It's very famous argument. So there's no such thing as the correct model. So all models are wrong, but some are useful. So I mean, in your analysis, whenever you have like troubles or problems fitting the data, just think about that if you can retransform the data or take care of the outliers. Yeah. So I think like in some of your projects, some of you really have like a very significant outliers problem. And I'm pretty sure that those would affect your analysis. So my suggestions, I think I wrote for you in the email, is that how about you just first throw away the outliers and consider the time series before the outliers, okay? And then we can just include the outliers and see what happens. So that's my suggestion if your data has some outliers. So do not first like include the outliers in your analysis. That would make you find a very like unreliable model. Okay, so that's some final thoughts, I think, for the S-ARIMA model. So any questions? Okay, so if there's no question, I think that's it for today's class. And starting from next class, we will start some new topics. Okay, so which is very interesting. So I think I will see you next class. Okay, thank you.
Thank you.